All right, let's go ahead and get started. Did y'all see my note about office hours? Okay, for those of you who didn't, or just a reminder, the MCC, room 303, upstairs on the third floor. It opens Tuesday of next week. So starting then, every Tuesday I'll be there from 2 to 4, and every Wednesday I'll be there from pretty much right after this class from 10:30 to 11:30. So if those times work for you, great, come see me. If they don't work for you, two things. One, make appointments with me. I am totally open and able to do that with you. If my times don't work for you, it'll probably be a remote meeting, especially if it's not like at a time that I'm like that I would otherwise be on campus. But I will meet with you. Or the MCC is open from 9:30 to 5 every single day. Literally everybody in there has taken Calc 2. I think as I said before, everyone in there is a PhD math student, which means at a minimum they've taken 371. So they can help you. So even if I'm not there, there's ways for you to get help there. Cool. All right, so that starts next Tuesday. Any other questions about what's going on? We have something to do tonight, yeah? Okay. So written homework is due tonight. On campus. Let me know either after class or sometime later if you have questions with that. Otherwise, let's go ahead and finish off this section. So as we talked about last time, the big thing here, we're trying to decide what substitution to make using trig. We're basically looking at which of the Pythagorean identities is going to allow us to take that expression under the radical and simplify it. So as I teased last time, we're going to have these three different forms we're going to primarily deal with under a radical: a squared minus u squared minus a squared, and u squared plus a squared. And basically those will dictate what kind of trig substitution I want to use. So we chose cosine for this case. Why did that work? What happened to that radical when we said that x is equal to 3 cosine theta? I hear something, but I can't tell what it is. What did that do to that expression under the radical, or to the radical itself? Simplified it, so the radical's gone, right? So that's essentially what we're doing. If we can get to a place with those two terms, we have two terms in the radical, right? If we can get that down to 1, we can evaluate the square root hopefully more easily. So keeping that in mind, let's look at another one of these forms. So let's really focus in on that radical. We have x squared plus 4. So what are our big three Pythagorean identities here? Most fundamentally, sine squared plus cosine squared equals 1. Divide everything by cosine squared and you get tangent squared theta plus 1 equals secant squared theta. And finally, if you divide everything by sine, you get 1 plus cotangent squared of theta equals cosecant squared of theta. So one of these is going to be our guide to kind of deal with that radical. So, and just to remind you, this is the u squared plus a squared form, as opposed to we had a difference last time. Go ahead.
I have a question about the last one. Could we have used sine for the cosine?
I believe we could have. Yeah, I don't think I have time to convince you that right now, but I'm certain that would have worked. In fact, I think if you look at the textbook, that's probably I think that's their preferred way to do that, but it doesn't really matter. All right, so x squared plus 4. What trig function could I align x with to make that work? I gotta vote for tangent. Let's try it. So x equals tangent theta. If x equals tangent theta, then what are we gonna wind up with? Let's just look under the radical. Yeah, so if we look under the radical, that's going to become tangent squared theta plus 4. We're gonna run into the same problem where our constants, our coefficients differ. So what if instead of tangent theta, we make it 2 tangent theta? How do we choose 2? Where'd that number come from? Square root of 4. So now what's going to happen to this? If I use this substitution, first of all, if 2 tangent theta is x, what is dx? Okay. So based on that x, I believe that is what dx has to be. If we follow this kind of translation, what does our integral become?
Over 2 tangent squared.
Close. 4 tangent squared theta. And the radical becomes radical 4 tangent squared theta plus 4. All of this times dx, which is 2 secant squared theta d theta. Is it obvious at all if that was the right move? Go ahead.
Why is it 4?
Which one?
Like 4 tangent squared theta.
Inside or outside the radical? Actually, it doesn't matter. I guess they're both x squared. So if you square x is equal to 2 tangent theta, right? I have to square all of what x is.
Oh, okay.
So if x equals 2 tangent theta, then x squared is equal to 2 squared tangent squared theta. All right. Is it obvious at all whether that was helpful? Go ahead.
How do we get tangent? Tangent theta again?
That's a good question. I didn't come up with that. I should have asked this, but why did we say tangent theta was? Whoever made that choice, what was that based on? Or if it was a guess, that's fine. It'll be easier to explain why that didn't work after we're done, but I kind of want to know now if there's a reason.
Because you can factor out the 4 and substitute the tan squared plus 1 for secant squared.
Okay. So I think that's kind of how this form of radical u squared plus a squared dictates the trig function is going to dictate, is because it is going to allow for that simplification. So I'm going to do what was suggested. We'll do small steps here, but 4 tangent squared theta times the square root of 4 times tangent squared theta plus 1. Is it okay to save space? I put all this stuff up here. Okay, so now that we factored out that 4, what do I know about tangent squared theta plus 1? It's secant squared theta. So the integral of 2 secant squared theta over 4 tangent squared theta times the square root of 4 secant squared theta d theta. So the whole point of this, remember, was to stop having to deal with that radical. So this becomes 2 secant squared theta over 4 tangent squared theta times 2 secant theta d theta. Is it obvious yet whether that was the right call? The x equals 2 tangent theta. Is there any more simplifying we can do? What can I simplify? Coefficients 2 and 4. Yeah, that becomes 8.
The secants, you can cancel one of them.
Yep, so. I think that's true. Can we go any further? Here's one thing that I like to do if it's not clear what the way forward is, and right now I don't think it's very clear at all. I think let's go back to sines and cosines because those are probably where we feel most comfortable. What is secant in terms of sines and cosines? 1 over cosine. So this becomes 2 over cosine theta. What's tangent in terms of sines and cosines?
Sine squared theta.
Also, would you all be offended if I did this? Took a 1/4 out of here. Okay, you like to bring constants out of the integral, so we'll do that. So one of these becomes 1 over cosine theta. What does the 1 over tangent squared theta become? I believe that comes cosine squared theta over sine squared theta. Is that helpful?
Why are you multiplying it?
Why am I multiplying? So after I pull out the 1/4, basically what I have to deal with left is sine, or sorry, not sine, secant in the numerator and tangent squared in the denominator. So basically what I'm doing is I'm treating them like this. Secant theta times 1 over tangent squared theta.
Okay. So 1 over tangent. 1 over tangent is equal to cosine squared over sine.
1 over tangent squared is equal to, so let's break it down. Tangent is equal to what in terms of sine and cosine? Sine and cosine. Sine over cosine, right? Which means tangent squared is sine squared over cosine squared.
That's cotangent, right?
Right. So 1 over tangent is cotangent. So that's why I have the reciprocal there, cosine squared over sine squared, because I have 1 over tangent squared. If I was multiplying simply by tangent squared, then yeah, you would see the reciprocal. So now that I have this thing in terms of sines and cosines, I lose that cosine, I lose a power of cosines here. And I have 1/4 times the integral of cosine theta over sine squared d theta. Are we stuck or can we finish this? Go ahead. I would love to do U substitution. What U would you like to use? If U equals sine theta, what does du equal? Cosine theta, yeah, d theta. So yeah, we had 2 layers of substitution here. I've run out of room. So let's stop and talk about what the way forward is. Do we think that U substitution that was just brought up, will that take us to where we want to go? Yeah. Okay. Let's do this. Since I'm kind of out of room, let's set up the integral and see how we feel about that. So based on this, I believe this becomes 1/4 times the integral of 1 over U squared times du. First question, do you agree? Or do we need to break something? That we took a long journey here. So if we got to stop and develop something, let's do it. Okay, question 2. Can we finish this integral based on where we are right now? Do we know what the integral of 1 over U squared is with respect to U?
Yeah.
Yes. There's probably a way I could rewrite this to make it jump at you a little more. But 1/4 times the integral of u to the -2 du. How are we doing? Yeah, this thing is badly organized. So started here, went this direction for a while, jumped over here, and then went up. Yeah, this is nasty. The reason I'm drawing those arrows is I'm gonna do one more. Give you a fighting chance of trying to decompose this later. What is the integral of u to the -2 with respect to u? -1 over u to the -1/1. So this becomes 1/4 times 1 over u, -1/4 times 1 over u, plus c, which finally is -1/4 times 1 over what? Sine theta plus c. So a long way to go for that. Ask me all the questions. Go ahead.
And square plus 1 because. I mean, we choose tangent because tan squared plus 1 like this the u plus a.
Right. So basically, so this all came from, you know, those three forms I talked about. Those three, basically, what does the expression under the radical look like?
Yeah.
This one, I have this two squares added to each other. That fits with your substitution being based on a tangent.
Yeah.
Because then that lets you go to secant squared, and then the radical goes away more easily. Go ahead.
Do they have to be under like the?
Those are the ones we're gonna deal with.
Yeah, but like if it was just x squared square root of x squared plus 4, would we also use them?
I don't believe it's zero. So why? So let's think about why this works. So let's say we had just x squared times x squared plus 4, and we tried the same substitution. Then maybe get 4 tangent squared times 4 tangent squared plus 4.
Oh yeah, we would be able to like cancel it.
You'd be able to get down to a secant squared, and maybe it would work, but I'm not sure without actually like trying to go through and do it. Yeah, you might need some other techniques, but I'm not totally sure. Go ahead.
Shouldn't the last u be cubed since it's in the denominator?
Be cubed?
Yeah. Because before it's squared, then you do.
No, so. If you think about the way, so basically this is the power rule of integration. Power was -2, right? So when you take the antiderivative, you raise the power by 1. Which makes it -1. But yeah, right, so. And that's like kind of a subtle thing here. You see 1 over u squared. You know, in one respect, yes, the exponent is 2, but it's really all about. Multiplicatively with something. This is not really u squared. We're going to divide 1 by u squared. So we're going to treat with the exponent a little different. Go ahead.
So what if we're just going to go to like before you like change everything again, and we still take the 1 foot out, but instead of instituting everything because we just substitute it down for you can square it right into that.
That probably would have worked as well. So you're asking, I think we go back to maybe here. What would happen if we, so tangent squared of theta equals what? Equals secant squared theta minus 1. That is true. I'm not sure where you go from there because then you have a denominator that has multiple terms in it. Those are inherently harder to deal with. I'm not gonna promise you this is the most direct way to do this, but I think it is.
When you, do the use of then.
Yep.
Why isn't it, cosine of u squared instead of, one over u? Why is it one over u squared instead of cosine over u squared?
Because remember, when you choose a u for your substitution, you also have it as a consequence of that what du is. So if u is sine theta, then du is cosine theta d theta. So the denominator becomes u squared. But then this numerator, or this numerator and multiplied by the d theta, that collectively makes up this du. So a reminder about integration by substitution. You can't do the integral. So in general, we cannot do integrals in terms of more than one variable. So if we're going to do a substitution and make it work, you have to get rid of everything that is expressed in terms of the old variable. In this case, theta, in favor of the new variable u, which we did. But yeah, that's just a reminder. You got to make that transformation on the variable, the differential of the variables, so the d theta, and if there are some, the limits. There are no limits in this case. How we feel? Besides, this was nasty. It's got away from us a little bit. I'm not surprised, but if there are any more questions, please ask. I know we just went through a lot together. All right, this one's too similar to do that. But one thing I do want to point out is I told you there are 3 forms of this. We've looked at 2 of them. This one is sort of similar to the first one, but now we're looking at this u squared minus a squared form. So again, sine squared theta plus cosine squared theta equals 1. As I'm writing this, think about what substitution you would like to make now. What is going to make that radical go away?
I think sine.
Sine? Let's try. So x equals just sine theta? Something else? Yeah, let's try 10 sine theta. If we do 10 sine theta, then what does dx become? 10 cosine theta d theta. And this integral becomes the integral of 1 over the square root of 100 sine squared theta minus 100 times 10 cosine theta d theta. All right, this whole thing, whether this works, all hinges on what's going on with the radical, right? Are we going to be able to simplify that radical with where we are? I hear a vote for yes. We factor out the 100, we get sine squared theta minus 1, right? What is sine squared theta minus 1? Negative cosine squared. Then you have the square root of a negative cosine squared. Negative cosine squared will always be negative, right? If I take the cosine of an angle, that can be positive or negative, but I'm going to square it. That's never negative. So multiplying them by, so sticking a negative on it is going to make it negative. I don't think this is going to get us there. So basically what we're looking for is where is the, variable squared minus 1 going to come from? Cotangent? So are you saying that this should now be, so let's start over. So let's do some investigation here. If I solve this for cosecant squared, no, it already is. If x is 10 cosecant theta, what is dx? I think it's -10 cosecant theta, cotangent theta, d theta. All right, so let's look at it. Based on that, we have 1 over the square root of 100 cosecant squared theta minus 100 times -10 cosecant theta cotangent theta d theta. How do we feel now? What does the radical become?
100 and then cosecant or theta minus 1.
Does that help?
Cool.
What is cosecant squared theta minus 1? Cotangent. So that's the way to go. That's a way to go. Again, I think actually in the book they lean into secant theta, which also works. So now that we can use Pythagorean identity to swap that out. We're going to get -10 cosecant theta cotangent theta over the square root of 100 times what? Cotangent theta, right? Cotangent squared. And that becomes -10 cosecant theta cotangent theta over 10 cotangent theta d theta. Okay, I'll stop there to let you all drink it in. First of all, do we agree with the things that have happened, that they are mathematically accurate and true? They might not be. I make mistakes. If we're convinced that what we have done so far is right, is it useful? Can we make some more simplifications to help?
This next tangent be
It cancels?
Yeah.
Yeah. So now we have also tens. So the negative integral of is it really just cosecant? Okay. Not an integral I know off the top of my head. You can, but I don't. So what does it become in terms of sines and cosines? So yeah, that's true. I don't see where to go from there. So I'll give you a couple options, and either one's fine with me. We can integrate, even though we don't know what the integral of cosecant theta is, we can integrate it. I don't think we do U substitution, because I don't think the derivative of cosecant theta is simple enough to, like, the d theta is not going to be able to help you out there. So actually, here are the two options. I'm going to choose option 2 because I want to. Option 1 is we can do integration by parts, because I believe we could find the derivative of cosecant theta. I think we could do it by hand, and then we could set up integration by parts that way. Option 2 is I Google what the integral of cosecant theta is. Go ahead.
Similar to our trigonometricals. Honestly, I don't remember.
So here is what I am finding. The negative natural log of cosecant theta plus cotangent theta plus c. So here's one thing I have a concern about. As I said, the book kind of leans into not using cosecant for the substitution. They kind of lean into using secant. And I have a suspicion that comes out, that it ends up in a place that's more manageable. So can we take a quick look at what that would look like? Okay, we'll kind of fast forward since we've already gone through it, but let me do something here. Take this slide, make a new one. All right, so we did x equals 10 cosecant, right? What if we do 10 secant theta? Which means dx is equal to what? 10 secant theta tangent theta? D theta? Which means the integral goes what? 1 over the square root of 10 times. Sorry, not 10. I'm working ahead of myself. 100 times secant squared theta minus 1 times 10 secant theta tangent theta d theta. With me so far? What is secant squared theta minus 1? Tangent squared, right? So then the denominator becomes 10 tangent theta times 10 secant theta tangent theta d theta. Tangents cancel, tens cancel. So then you have the integral of secant theta d theta, which I don't believe is any simpler. So yeah, from there you can rely on integration by parts, or once we've gotten to this point, the biggest thing I'm worried about with this new unit, this new section, is what's the trig substitution that gets you to something more manageable, which I believe we've done that 2 different ways now. Do you have a question?
I was gonna say the integral of secant is a lot like the cosecant. It just
Yeah, I suspected it would be, which is kind of to say that just by their relationships, you know, for the first one we looked at, like I said, the book prefers sine. I think we did cosine. I don't believe it. I think all the differences that it made were cosmetic. I think that the process was the same, the rationale was the same, and I suspected the same was going to be true for secant and cosecant. How are we feeling? Want to put it behind us?
For example, you want us to keep going, or can we leave it like that?
No, we don't want us to keep going. Here's why I went through this and why I did it quickly. I wanted to see if this would give us something like significantly more manageable than this, and it didn't. So we have ways to integrate cosecant and secant, but I don't think directly, unless you happen to know what that antiderivative is. I didn't remember what the one for cosecant was. At this point, I'm happy with you. At that point, like once you facilitate the integral, I'm happy with you looking it up. I know some of you are thinking, well, what if that happens on a test? It won't. That's not my goal to test your memory of really obscure integrals. Doesn't make any sense. All right, so let's put that section behind us. On to 6.3. So we're talking about integration of partial fractions, which maybe is something you've dealt with in the past, not integration of them, but basically how to do partial fractions. So to kind of motivate what the heck that is, let's look at this thing. I want to write this as a single fraction. If I want to write that as a single fraction, what do I have to do? The denominators have to be the same, right? So I got to find a common denominator, which I don't have right now, but what would a common denominator be for these two fractions? Right, they they don't really have anything in common in the ways we would want, so our really only hope is to, well, I'm sorry, they do have something in common, the 9, but really the common denominator is going to have to be 9 times x plus 4 times 2x minus 1. I'll duplicate that because I have two different things going on here. I'm going to transform both of them one at a time. So basically, the first thing I would like to do is rewrite these two fractions so that they can share a common denominator. The first numerator of 4 is going to change, but how? How do I make those changes? Why are we multiplying by 2x minus 1? Right, so yeah, algebraically, whatever multiplication I made to the denominator, 2x minus 1, I have to do to the numerator. So similarly, what am I multiplying the 1 by here? X plus 4. So let's do some expanding. 8x minus 4 over 9 times x plus 4 times 2x minus 1 plus x plus 4 over 9 times x plus 4 over 2x minus 1. Can I combine these now? How do they combine?
First, we can simplify the denominator.
Simplify the denominator. I'm going to keep it like that. I'm going to keep it factored. But yes, we absolutely could do that.
9x over the combination.
How'd you get 9x?
It's the new expression would be 8x minus 4 plus x plus 4.
Right. So that's kind of the whole point of finding the common denominator, right? Now that I have the common denominator, I can simply add their numerators together and I get 9x over 9 times x plus 4 over 2x minus 1, which is equal to x over x plus 4 over 2x minus 1. And yes, somebody brought it up. We could expand the denominator. For now, I'll just leave it factored. But I think we you started doing this with much simpler fractions when you were very young, but adding those together is something you've done in the past. Maybe not. Maybe we have not done the opposite. So I want to integrate this thing. I think I made a mistake here. I wanted these to be inverse. Okay. So I want to integrate this thing, which is not something we can do directly. Basically, what we have to do is do the opposite approach. I want to pull that fraction apart. I have one fraction. I would like to be able to break it down into multiple simpler things. So before we can start integrating, we have to decompose this. And based on what we just did, we should know where we're going to end up, but let's kind of look at what the process looks like. So now let's think about this. I want to break this fraction that, let's look at it this way. This thing that I have here that I've written down in red, let's assume this thing was found by adding some other fractions together. So now what we have to think about is, what might those fractions have looked like? What denominators could they have had? In other words, what denominators might I have been dealing with that led to this common denominator?
Well, one of them might have found x plus 4 and then the other found 2x.
Right. So basically, that's kind of how I'm going to set this up. I'm going to assume that this thing came from one fraction whose denominator was x plus 4, added to some other fraction whose denominator was 2x minus 1. We know in reality that's how we got that, but let's pretend we don't know. So yes, I believe that if I added those two fractions together, I would wind up with that common denominator, right? Are there any other denominators that could have been involved here? Maybe coefficients, but that'll all come out when we figure out what those A and B actually stand for. But really no other, so we had a suggestion a while ago to expand that, so that would come out to be 2x squared plus 7x minus 4. If I ask you to factor that, is there multiple ways to factor that? Now, if I give you a quadratic, there's only one way to factor that. Sometimes there's not a way to factor it, but at most there's one unique way to factor. Like, aside from like multiplying by coefficients, there's only one way to do it. So this is what we have. Now we want to figure out what A and B are. Just curious, is this a process that people have seen before? Okay, a couple. So how do I figure out what A and B are? First thing I'm going to do to make this thing simpler to think about is I'm going to clear the fractions. So how can I get rid of all the fractions in this equation that I've set up? Multiply by what specifically? Everything that's making fractions happen, right? All the divisions I'm doing. So if I multiply everything by x plus 4 times 2x minus 1, then the left-hand side of this equation becomes x. The right-hand side of this equation becomes what? What happens to this first fraction here? What happens to a over x plus 4?
Be canceled now and just leave 2x minus 1.
Right, so I have a times 2x minus 1. And similarly, I have b times x plus 4. So now here's how I'm going to find out a and b. On the left, I have essentially a polynomial. It's just x. On the right, I have a polynomial. I know those polynomials are equal. What's the only way that those polynomials can be equal? So let me do some expanding here. X equals 2ax minus a plus bx plus 4b. Let's also kind of group things up. So these things have x's. 2a plus b. And what things are a constant? Plus negative a plus 4b. So on the left, I simply have x. On the right, I have some terms that have x and some terms that are constant. What is my x term? Like, what's the coefficient of my x term on the left side of this equation? It's 1, right? What is the coefficient of the x term on the right side of the equation? Is it 1? Doesn't look like 1, but it has to be 1, right? That's the only way they can be equal, is if the coefficient of the x terms are equal on both sides. And what about the constants? They have to cancel. So meaning if I add them all up, then what has to happen? What does their sum have to be? 0. So based on that equality, I know that my coefficients for all my x terms have to be equal to 1. And all my constants have to annihilate each other, which means if I add them up, I get 0. Can we now figure out what a and b are?
Can you explain that? I didn't.
Yeah, the coefficient thing here?
Yeah.
Yeah, let me give you an example over here. So let's put in some more concrete numbers. Let's say I have 4x plus 2y minus 9z equals ax plus by plus cz. So I have 3 different variables in the thing I just wrote, x, y, and z. I have a, b, and c, which I'm telling you, they're not variables. We don't know what they are, but they're not variables. They're constants that we don't know. We just don't know what they are. But I'm saying something very strong, which is that the left-hand side of that thing and the right-hand side of that are equal. There's only one possible way I can really have equality there. And if I really have equality there, what is A?
Okay, so we're trying to like bring it back to the initial equation, like to make it look like that, kind of.
Basically, yeah, I'm trying, this is called partial fraction decomposition. I have this complex looking algebraic fraction, rational function. And if I can, I want to pull it apart so that it's a sum of simpler looking fractions. So we're kind of started out by supposing that this thing I want to integrate is actually the sum of things that look like this. But now if we, going from there, we have to figure out, we know something about what the denominators look like. Actually, we know everything about what the denominators look like. We don't know anything about what their numerators look like. That's the point of the rest of this.
Okay.
Any other questions?
If it was like on top, it was like 9x, let's say, on the integral.
Yep.
Would our 2a plus b equal to 9?
Absolutely.
Okay.
Yes. So, yeah, the big bottom line there is that to have equality on either side of that equal sign, the number of x's I have on left and right have to be equal.
Okay.
The number of constants, that we say, the number of constants I have on either side have to be the same. On the left-hand side, I have no constant. So on the right-hand side, I have to have no constant.
Would that be like a +5 at the end or something like that, or what?
Yeah, so I mean, it's not obvious, it's not as obvious there are constants on the right-hand side because we're calling them A and B.
Uh-huh.
A and B are constant, I just don't know what they are yet. I can figure it out. X is the only thing that can really vary and be different values. So now I have this system of two equations. Can I figure out what A and B are now based on those two equations?
Could you like solve for like the U of A and then plug that into the R next to
Sure, how do you want to do that?
so like subtract 2a, and then you get b is equal to 1.
B is equal to 1 minus 2a. We agree with that? And then what do you want to do with that thing you just found?
Plug b into all our b terms.
No, if you plug that back into the equation you got it from, you're gonna wind up.
Most of those are all in terms of a. That's what I.
Oh, okay. So solve the top equation for A.
Well, now you can plug b in as 1 minus 2a for all our terms of b in that equation. So now all our variables are in terms of a.
Okay.
That's what I thought.
So this thing you just found, I believe, so you use the top equation to make this.
Yes.
So I think if you put this back into the top equation, everything will cancel.
Back into like our equation on the left. That equation cancels.
Oh, okay. So I'm going to modify that by doing this. So I'm going to put this B you just found into the second equation. So minus A plus 4 times 1 minus 2A equals 0. Now I have an equation with a single unknown in it. So minus A plus 4 minus 8A equals 0. 4 equals 9A. A equals 4 9ths, right? So I got one of them. We're not going to finish the integral, but real quick, let's get B. If A is equal to 4 9ths, what is B equal to? What's that? How'd you get that?
The negative a plus 4b.
Okay, you could also do that, or this thing right here is a really easy translation map. If we know A, we basically have a formula for B. So A equals 4 9ths, B equals 1 9th. And to kind of set this up for next time, that means the integral we really want to do is this. The integral of 4 9ths over x plus 4 minus 1 9th over 2x minus 1. And we'll talk about, some of you might already see the way forward now that I've written that down, but that's basically the whole point of this process. We have no hope of doing the integral I started you with. Some of you are kind of already seeing it in your head.
It's a minus on a plus.
We said B was negative, right? Or do we say it was positive? Okay, that's confusing, yeah. Keep it plus. Thank you. How we doing? All right, cool. We'll finish this up and do some more of these on Friday. No, you're fine. So what was the function we were doing? Was it 1 over radical? Yeah, that is, if we're taking derivative, yes, that goes to our. Oh, no, you're right, that includes, yeah, you're right, that's what parts on which.
A homework question, and it's like on a written program. Would you, like.
Do you offer honors contract?
Yeah, I think you need that.
Oh, I didn't get.
So. Short answer is yes, so we have a course coordinator, so I'll have to work with her, like. Full attention to supervising it on paper, but yeah, so basically what I said, was, yes, short answer is yes, we do. I'll let you kind of think about what direction I'm taking, and that might be a hard thing for you to figure out, and so we do a little bit more in here, but yeah, absolutely, I don't know, what do you know when I was conference? Well, you got how you're proposing a little bit.
It's, I think I have to submit by like the 14th.
Okay. So yeah, let me know, so if you have any ideas right now, kind of send those to me over email right now, and I'll kind of. All work, we will bounce back and forth and find.
Okay, yeah, that's great. I didn't get the email.
I'll make sure I hit send, make sure it's not sitting in my drafts, but. Yeah, I remember writing it, for sure. Hey,
You just need again 5 days of plus 14 has to be.
yeah,
Yeah, I didn't get it.
okay, I'll make sure I.
Maybe somewhere.
Okay, let me rewrite this equation. So. X, I can really think of this as this 1x plus 0 equals a times 2x minus 1 plus b times x plus 4. So after I expand all this stuff, basically I know that everything over here that has a variable x attached to it has to agree with all the things that have a variable x attached to it here. Everything that doesn't have a variable x attached to it here has to agree with all the things that don't as well. I think the subtle thing that makes this tricky is there's nothing on the left hand side that isn't governed by x. There are no constants on the left, which means that anything that comes out, anything that is like independence of x over here is eventually going to vanish.
Okay.
So I think now that we found a and b, this becomes negative 4 nines plus 4 nines, right? Which is, that's going to make all my constants vanish, just like
Over here.
the left hand side. And this shit.
And there was something over there.
Yeah, this is like x plus 10, then that means
Yeah.
this thing right here equals 10.
Okay, thank you so much.
I think you need to know.
Yeah, I responded to like 30 minutes before we came in. So you said 2:30, right?
Yeah. Thanks.
I had a homework question
Sure.
too. I was doing this.
Okay.
There were all of these, I had one. Yeah, essentially cosine squared x,
Okay.
and I got stuck and then tried using Google, and it basically said it to like. Use the usual. Add one to the exponent and divide by it,
No.
and I was like,
So
I don't know where to go.
if you want to look at your notes from when we did this, I think one of the early things we did was getting rid of cosine squared. And the way we made it work is by the double angle identities. So
Well, we did a sine square with the double angle identity,
we have,
but I didn't know.
so we spent 3 days in that section. I think it was like the second example in the first day.
Yeah.
But this thing is really powerful because of all the different forms it has. So cosine of 2 theta is equal to cosine squared theta minus sine squared theta. Or 2 cosine squared theta minus 1, or 1 minus 2 sine squared theta.
I think I might have, would you use the, right, no, no.
What were you gonna say?
I was gonna say, I don't remember, cause I looked back at my notes and I didn't remember seeing the top one. But I was
It's
gonna say,
it's true, but it's like not terribly useful.
yeah,
Because typically we're trying to transform. You either have a cosine squared or a sine squared that's causing problems, it's not usually both. So typically we go for one of these.
Okay.
So knowing that cosine 2 theta equals this. You can't integrate this directly, but if you isolate it, you can solve, you can put this in terms of things that can be integrated
okay,
more handily. So I think I put on Canvas, if I didn't, I put an announcement like, basically I just took a screenshot of the formulas I'm going to give you on test 1,
okay,
and it's. I think it's the same ones we're talking about, the Pythagorean identities, and the double angle identities.
sweet, thank you.
Of course.
Can I ask you one other quick thing? There was also one that was, I think it was signed to the 4th, X, yeah. And I was trying to do that one as well, but I got stuck because I thought. I was trying to get, do it, but there's like the one sign left over that you can sort of get
Yeah.
the X, but it doesn't work.
You're not gonna get that, so,
So,
again, I think you're gonna have to go here, knowing that. So if you can isolate sine squared, right?
Yeah.
And then whatever you wind up with, you can square that.
okay.
Um,
Oh,
so,
gotcha, okay,
I think,
yeah,
and kind of looking downstream, I think once you do that, you might have to get double angle identity again.
okay,
But eventually you can turn sine of the 4th into. A bunch of cosines that are not squared, their angles might be doubled in quadruples, but they won't be squared, so you can integrate.
okay, gotcha. Sweet, thank you.
Yeah, of course.
So multiple questions on the homework, do we have to apply double angle identities?
At least one, I can't remember how many, but I'm sure there are multiple times you have to do it.
Definitely got stuck on a couple of them, I wasn't sure where to go from there.
Yeah, so the big. I'm not gonna promise it's the only one, but I can't think of another one on the top of my head. The big reason the double angles become useful is because. There's a big difference between this integral, cosine squared theta, sine theta d theta. You can set up a substitution for that. U equals cosine theta and then du equals this. Or a version of this. As opposed to this thing. Which there's no way home with the substitution, so you have to rely on this thing. So I don't know, it kind of comes to practice which ones you have to use, but if you see squares of trig functions, Pythagorean identities and double angle identities are going to be the biggest things you lean on instead of start re-expressing it.
Okay.
Or picture, or yeah, whatever. Yeah, so there are other tutoring centers. The one I'll be in is in room 303 upstairs. Thank you.
I mean, like, let's say you weren't there, just for general.
Yeah,
You're also in the
someone's working there all the time from between 9:30 and 5 when it's open. So we all wear like these purple lanyards. If you, any one of us can help you.
Did you, the engineering tutoring center, like, did it